I am an astrophysicist and former research director. I have spent my entire career at the French Centre for Scientific Research, the CNRS. I lead a small group of researchers, physicists and mathematicians. We are working to develop a new cosmological model which we have named after the god Janus. The purpose of this 90-minute video is to present in a single document both the basics of the model and the many developments to which it has given rise. This model attempts to provide coherent response to the crisis that astrophysics and cosmology have been going through for decades. Hypothesis-laden disciplines called inflation, dark matter, dark energy, where science is now conjugated in the conditional, populated with words like could, would be, would explain. This video consists in a set of hundreds of numbered sentences that form a text file which they were given in both French and English, downloadable at the address below. This is intended to allow translators to provide the translation of these sentences in their language, number after number, in a sound file which will then allow us to create a version of this video, not subtitled but dubbed. We are going to start by talking about this crisis in both astrophysics and cosmology. Starting in the 70s, it was possible to plot the rotation of gaseous matter inside the galaxies. Those gaseous elements were following almost circular orbits within the gravitational field of a given galaxy, as well as for stars in the galaxies such as our Sun. Here is the rotating curve of our galaxy, the Milky Way. Here we have spotted the speed of the Sun on its circular orbit, roughly 220 km per second. As seen below, the curve representing the circular speed where the centrifugal speed is balanced between the gravitational field. This gravitational field being calculated from the mass within the galaxy deducted from astronomical observations. As far as the Sun goes, we observe an excessive speed of about 60 km per second. As such, the Sun should be leaving the galaxy due to the centrifugal force. As a matter of fact, the whole galaxy should be scattering because of that. Based on those facts, astrophysicians deducted that galaxies must be hosting some kind of matter that is escaping from optical observations. They named it dark matter. Galaxies gather in spheroidal clusters that sometimes are constituted by several thousands of galaxies. Speeds of galaxies in those clusters cannot be moved by a speed greater than the release speed, which value is proportional to the square root of the cluster's mass. Here again we find that galaxies are moved by speeds exceeding this value. Astrophysicians deducted that a large amount of dark matter was preventing the galaxies from leaving their clusters. Therefore, before 1990, the total of dark matter at the scale of the universe was represented by the percentage on this chart. We therefore tried to identify the nature of this invisible mass, but it was still resisting any kind of observations. Starting in the 90s, speed measurements of shrinking galaxies located very far away have been done. They were providing that the expansion of the universe was accelerating instead of slowing down. The Nobel Prize was granted to Perlmutter, Schmidt and Rice for this discovery. We stated that this phenomenon would be explained by the presence of a mysterious dark energy, negative and repulsive. The percentages of those new elements were now reading like this. The observable piece of the visible matter fall down to 4%. Since 2011, theoreticians integrated those new data in their own way and coined a new model, the delta CDM model. CDM standing for cold dark matter meaning a dark matter which components have weak speeds of thermal agitations compared to the speed of light. Delta referring to the cosmological constant which they decided to include inside Einstein's equation, an equation term supposed to be referring to the mysterious repulsive power of the void. Another idea was proposed by Dr. Mordecai Milgram, in which Newton's law was supposed to be modified after a given distance, going from 1 divided by r squared to 1 divided by r. This change would yield curves of circulatory orbital speeds being flat where it was needed, at galaxies' suburbs. But this law, having no theoretical grounds behind it, had to match also other situations. It turned out one would have to modify it again in order to fit the clusters of galaxies' observations, which would mean that this new law would modify according to the distance but also according to the mass involved. Then some theoreticians turned to an old idea telling about a universe filled with positive masses and negative masses. This was considered in 1957 by a cosmologist named Hermann Bondi. This approach gave out a rule named the runaway paradox. We shall explain the origins of this paradox. Just like Bondi, we assume that the universe is ruled by Einstein's equation, coined in 1915, more than a century ago. This signification of this equation is that the local geometry of the universe is determined by its content of matter. It relies also on the idea that test particles are following geodesics running on the time-space hypersurface. What creates a gravitational field is represented by the second part of this equation. If we consider that in one given region a positive mass contained within a sphere will create a gravitational field around it, it will imply that any witness particle evolving around this field will follow this geodesics, evoking the attraction phenomenon. For any witness particle, whether it has a positive or a negative mass, which boils down to positive masses attract everything around its neighborhood. On the opposite, let us consider a gravitational field created by a sphere filled with negative mass. This Einstein's equation would produce trajectories suggesting a repulsion that witness particles would follow, whether they would have positive or negative masses, which could be summed up as negative masses repulse everything that goes near it. A negative mass will especially push away another witness mass which would also be negative. The paradox appears when we consider an interaction between a positive and a negative mass. The negative mass attracted by the positive mass would rush onto it, but its repulsive force acting on the positive mass makes it run away from it. We then get the pattern seen on this image. If the two masses are equal and opposite, they both accelerate in the same direction, keeping the same distance between them. It is clear that this interaction between particles of opposite sign comes in total violation of the action-reaction principle. If those masses are equal and opposite, they undergo a rise in speed with continuous acceleration, while the energy of the whole system remains constant. Indeed, if the kinetic energy of the positive particles is positive, the energy acquired by the negative mass is negative. We then stumble upon a second paradox. Particles see their speeds rising without any input of energy. We called this the runaway effect. The question remaining here is, will we accept to integrate this phenomenon in the new physics or not? Some people do so, such as the French physicist Gabriel Chardin. This person imagines that the negative masses would consist of primordial antimatter. It is worth to mention that this hypothesis cannot rely on the standard theoretical model. Along with another physicist, Aurélien Benoît-Lévy, they both are taking over this idea coined in 1930 by Dirac and Milne, stating that densities of those two components are equal and opposite, which would give an overall density of zero, therefore no gravity at all. This yields therefore a constant speed of expansion with no acceleration or deceleration, and which contradicts the 2011 observational data. Nowadays, some experiments are being held in the CERN in order to attempt monitoring the behavior of antimatter in the presence of Earth gravitational field. This antimatter is generated by the Great Particle Accelerator in CERN. Chardin hopes that this antimatter will fall upwards. Just like Chardin, Benoît-Lévy, the English physicist James Farnes, accepts that the cosmological model where the runaway effect occurs. They interpret this limitless acceleration as the origin of cosmic rays. In their interpretation of the fact that the negative masses repulse each other and repulse positive masses, they see a model of galaxies being confined by a negative mass environment, thus modifying the rotation curves, becoming therefore flat. In fact, a gap in a negative mass from a gravitational point of view equals a positive mass concentration. Therefore, the void in a negative mass layout holds the same role than a dark matter concentration, and Farnes recognizes that the flat aspect of the rotating speed curves. In those two models, the one of Chardin, Benoît-Lévy, and the one of Farnes, the principles of action-reaction remains violated when one considers the interaction of two opposite sign masses. It is impossible to escape from this paradox if we stand within Einstein's model, introduced 1 century ago and based on this equation, and matching a certain kind of cosmological geometry. Could it be possible to consider another model where the principle of action-reaction would not be violated? Once we would have placed witness particles in a given gravitational field created by a certain positive and negative mass layout, we would observe if the particles react differently according to their sign. Let's look into Einstein's equation once again. The source of gravitational field lays in the second side of the equation. The reaction of the witness particle can be read in the equation's solution under the form of a metrical function from which we calculate trajectories. That was shown here previously. In order for witness particles to react differently, one would need to see the gravitational field giving, on the first side of the equation, two solutions written as two metric functions, which would generate two different families of curves or trajectories. This is doable if one considers not one, but a system of two coupled fields equations. This was considered among others by Thibaut Damour, a member of the Académie des Sciences de Paris, and a professor at Institut des Hautes Études Scientifiques, which then produced a system of two coupled field equations. He then considered the most general interactions between two entities that he called right and left entities. In his model, these two entities are then supposed to interact through a spectrum of gravitons owning a mass. But beside having raised the problem under purely mathematical aspects, this attempt has never been produced by any tangible results. The 2008 attempts made by Sabine Hosenfelder, a scholar from the Advanced Sciences Institute in Frankfurt, is more advanced and comes out with the interaction laws. As we can see, the positive mass is referred to as the letter G, and the negative mass as the letter H. The action-reaction is not violated anymore, and one can now assume that the interaction between masses of opposite signs is consistent with anti-gravitation. But beside this result, she does not suggest any true model nor phenomenons which could be challenging and testing the validity of her hypothesis. In 2014, Jean-Pierre Petit and Descoutini proposed a system of equations very close to Hossenfelder's in an Astrophysics and Space Science article. On this article, they suggest right up front a total asymmetry between the two entities. In addition to that, they provide in their own cosmological model a conceptual aspect of the presence of these negative masses particle, therefore also to a negative energies. Their model relies on two starting points. To solve that, Sakharov imagines that the universe was composed of two aspects, geometrically linked by the Big Bang singularity. They would be two distinct spacetimes linked by one primordial dual singularity, each one of them having their own history, in a way that we would find each one of them a mix of quarks and antiquarks combining to become baryons and antibaryons. Baryons are protons and neutrons, while antibaryons would be antiprotons and antineutrons. As a reminder, according to the standard model, baryons are made of 3 quarks and antibaryons are made of 3 antiquarks, all being of positive energies, while antiprotons and antineutrons are made of 3 antiquarks, also with positive energy. In each aspect or fold of the universe, we initially find a mix of quarks and antiquarks. Therefore, in what Sakharov names a twin universe, strong and intense synthesis of matter and antimatter will take place at a high pace, starting from these mixes of quarks and antiquarks, and this occurring as long as temperature stays high enough in order for those syntheses to happen. That's to say, as long as quarks and antiquarks will carry enough energy to combine and produce baryons of an m mass, baryons and antibaryons of positive mass, therefore having an energy equal to mc squared. When the temperature drops, these syntheses stop and another mechanism takes over, the annihilation of antimatter-matter pairs giving photons. At the moment when these syntheses cease to occur, if those of particles of matter and antimatter have taken place at the same rate, these two populations annihilate each other and only photons remain. In our own universe, there has been an intense annihilation of these matter-antimatter pairs that have given rise to photons that make up the background radiation, whose radiation temperature is currently 2.7 degrees Kelvin. These photons are 1 billion times more numerous than the surviving matter particles. Sakharov's key hypothesis is to assume that in our universe the synthesis of matter from quarks would have been slightly faster than that of antimatter from antiquarks. Thus, at the moment when these syntheses cease with the lowering of the temperature, there would have remained 1 particle of matter out of 1 billion, plus antiquarks which could not have been combined to give antimatter, and this in a ratio of 3 out of 1. By simple concern of symmetry, Sakharov proposes that there is a second sheet of the universe where the contrary it is the synthesis of antimatter which would have been faster than the synthesis of matter. This twin universe would thus be composed of antimatter and a remnant of quarks, the whole being obviously immersed in a mass of photons from the annihilations. Sakharov then supposes that the arrows of time in these twin space-time would be opposite. This singular situation then acquires meaning thanks to the work of French mathematician Jean-Marie Souriau, who showed in 1970 that particles with positive mass and energy travelling backwards and forwards are in fact particles traveling in the past-future direction, but with negative mass and energy. In other words, the inversion of time is equivalent to the inversion of energy and mass. The model proposed in 2014, known as the Janus model, is equivalent to the folding of Sakharov model, as shown in the figure by making the two entities interact. Why Janus? Because of temporal inversion, the Roman god Janus looking at both to the future and to the past. This Janus model thus concretizes Andrei Sakharov idea by proposing another geometrical configuration. Negative mass matter then simply replaces Andrei Sakharov's twin matter. Its nature and how it contributes to the gravitational field and how it reacts to it was simply clarified. The interaction laws corresponding to what has been described above. The Janus universe therefore has two contents. One consists of positive mass matter and the other of negative mass matter. This is supplemented by a large quantity of photons of positive energy resulting from the annihilation of matter and antimatter particles of positive mass and photons of negative mass resulting from the annihilation of matter and antimatter particles of negative mass. To this must be added antiquarks of positive energy, which could not combine to give antimatter of positive mass, and quarks of negative energy that couldn't combine to give negative mass matter. Sakharov had imagined that in order not to be able to observe this antimatter of the twin universe, it was located elsewhere, and that its only common point was the Big Bang singularity. In the Janus model, this non-observance of this primordial antimatter is handled differently. Particles or antiparticles of negative mass signal their existence by emitting photons of negative energy, which our instruments cannot capture. Symmetrically, if there are observers made up of negative mass and equipped with instruments of the same nature, they cannot capture photons of positive energy emitted by our own matter. For each of these worlds, positive or negative, the other world escapes observation in the field of optics. These two entities interact only by anti-gravity, obeying the principle of action-reaction. The Janus model not only explains the non-observation of primordial antimatter by giving substance to Sakharov's idea, but also provides a complete description of these invisible components to which we give the names of dark matter and dark energy. These two names actually cover the same entity, antimatter of negative mass, the components of which are antiprotons, antineutrons, and negative mass anti-electrons. So there is not one, but two antimatter. There is a cosmological antimatter, negative mass, primordial and invisible, but also a positive mass antimatter, which had totally disappeared, but which we are recreating in our powerful accelerators. Hence a prediction of the Janus model, this antimatter of positive mass will behave like ordinary matter in Earth's gravity field and fall down. In 1992, the Janus model existed in draft form. Its authors, Petit and D'Agostini, simply tested the behavior of a mixture of positive and negative masses, obeying this interaction pattern, satisfying the action-reaction principle. They then sought to see how a mixture of these two entities would behave with equal and opposite densities and equal and opposite temperatures, since the temperature of a negative medium is negative. They then saw a phenomenon of joint gravitational instability develop. producing a percolation of the two masses then tending to separate. That said, if one were to consider identifying one of the entities to the matter of our observable universe, this would not correspond to what was observed. They then had the idea of introducing a strong asymmetry between the two populations, by endowing the negative masses with a much higher density. Again, from the point of view of a double tendency of gravitational instability, the positive mass tends to gather, as does the negative mass, in a phenomenon known as accretion. Knowing that the characteristic accretion times are like the inverse of the square root of the density, it was to be expected that the negative mass would be the fastest to give rise and set a regular spaced conglomerates. This is what their numerical simulations revealed as early as 1994, as the matter was then confined in the residual space, which gave it a deficient appearance. And this then corresponded to what emanated from the observation with large voids of 100 million light-years in diameter. The Janus model then provided the explanation for such large-scale structure, with invisible negative mass conglomerates located at the center of each of these cells. In 2017, the result of an enormous work of census and processing observations emerged, covering hundreds of thousands of galaxies, occupying a cube of 1.5 billion light-years on each side. This work was presented in the prestigious magazine Nature by Frenchwoman Hélène Courtois, Israeli Yudi Hoffman, Canadian Brent Tully, and Frenchman Daniel Pourhamed. It has been known since the 1930s that the cosmos is expanding, and that if we evaluate the velocity of galaxies based on their redshift, we obtain a velocity field corresponding to Hubble's law, according to which the rate of escape is proportional to the distance. Courtois, Hoffman, Tully, and Pourhamed based their measurements on the hundreds of thousands of galaxies by subtracting the Hubble field from the recession velocities. This gave them access to the speeds of these objects in relation to space itself. They got what we already knew, which was the existence of an attraction center, the Shapley attractor. But the analysis revealed, almost symmetrically with respect to the observation points, our galaxy, located in the center of the cube, an empty area. On the fringes of this region, the galaxies were in flight, and they called it the Great Repeller. It is quite simply the first manifestation of the existence in the center of this region of conglomerates made up of negative invisible mass. We must now evoke the gravitational lens phenomenon, highlighted as early as 1918 by the Englishman Eddington and confirming Albert Einstein's theory. According to Einstein's model, photons are sensitive to the gravitational field, thus a positive mass curves the trajectories of photons, like this, which focuses this light and has the effect of increasing the apparent magnitude of distant sources, as with a converging lens that concentrates light's energy. As early as 1995, it was shown that a negative mass could also act on the trajectories of photons with positive energy in a manner of divergence lens. This has the effect of reducing the brightness of remote sources. Thus the magnitude of very distant sources of galaxies with high redshift should be reduced by this effect. And this is what is observed for galaxies with redshift greater than 7, which are considered to be dwarf galaxies. Whereas these are normal-sized galaxies whose light is partially diffracted when it encounters and even passes through the negative mass conglomerates it finds on its way. So far as positive energy particles and positive mass particles in the case of matter interact with these negative mass conglomerates only by anti-gravity. These particles can freely pass through them, which is what the photons emitted by these distant galaxies do in particular. This reduction of the magnitude of remote sources represents a second point in favor of the Janus model. In general, theorists have difficulties to model the birth of galaxies by gravitational instability. This instability manifests itself immediately after decoupling, when the universe is 400,000 years old and matter deionizes and ceases to interact with ambient radiation. This matter then tends to gather together by gravitational instability discovered by the Englishman James Jeans, which translates into a phenomenon of accretion, the gathering of matter into lumps. In doing so, this material heats up under pressure forces that result from the heating within these objects and oppose the force of gravity, which tends on the contrary to condense them. An equilibrium situation is established where the forces of pressure balance the forces of gravity. The matter is then not sufficiently condensed and warm enough to allow fusion reactions to take place. In order for the condensation process to continue, the object must be able to dissipate this thermal energy by radiation.
A state of equilibrium is established where the forces of pressure balance the forces of gravity. The matter is then not sufficiently condensed and warm enough to allow fusion reaction to take place. In order for the condensation process to continue, the object must be able to dissipate this thermal energy by radiation. The amount of thermal energy to be evacuated is then proportional to the volume of what is considered a protostar, a volume which is like the cube of the object diameter. Heat that would be dissipated by radiation from the star surface, acting as a radiator, and whose area is like the square of the object diameter. Thus, the larger the object, the longer its cooling time will be, allowing it to create in its inside the conditions for fusion. Negative mass conglomerates are the seat of the same process and emit radiation in the form of negative energy photon emission in the red and the infrared range. For an observer made of negative mass who could capture the negative energy photons emitted by these objects, this is how this negative side of the universe would appear to him. We can therefore consider them as huge protostars that will never light up. These conglomerates are composed of anti-hydrogen and anti-helium of negative mass, where nucleosynthesis cannot take place. Thus, in this negative world, there are no stars, no atoms heavier than helium, no planets. Life is therefore absent in this world of negative masses. When negative mass conglomerates are formed, they sandwich the positive mass into plates which are thus compressed and heated. But this geometry, unlike that of spherical objects, is optimal for rapid cooling, which increases gravitational instability. Phenomenon which, thanks to the performances of modern computers, would constitute an interesting formation scheme for galaxies. It has been said that the material adopts the form of Lachner distribution comparable to joint soap bubbles. 3 bubbles meet along a line that will be, for matter, a long filament populated with galaxies. 4 of these bubbles meet at one point, and it is in these nodes that the clusters of galaxies will be located. This pattern is consistent with the observation. Wherever galaxies form, negative mass will occupy all the space between them. In these regions, the galaxies occupy kinds of holes in the negative mass distribution. These gaps in the negative mass distribution create a gravitational field equivalent to that which would be created by this positive mass distribution. Thus, negative mass ensure the containment of these galaxies by playing the role that the theorists had assigned to dark matter of positive mass. The rotation curves then have this look, like those presented in 2001 by Petit and D'Agostini, and the one obtained by Farnes in 2017. In the 90s, Frédéric Descamps' numerical computer simulations, starting from a rotating object inside a gap in the negative mass, gave rise to barrel spirals that were consistent with the observations. Whereas in the simulation carried out until then, numerical galaxies quickly lost their arms. Now they keep this structure during more than 30 turns. Thus, a dynamic friction with their negative mass environment can be considered at the origin of the constitution of spiral galaxies. On the curve, we can see a strong loss of kinetic moments at the time of the constitution of these objects, and that after their evolution is much more peaceful. Frédéric Descamps showed that the more negative mass density was strong, the more the spiral arms tended to bend, to the point of giving this shape of a car steering wheel that astronomers are familiar with. It is hoped that researchers will use this idea to carry out more sophisticated multi-population simulation, thus exploiting these mechanisms of galaxy formation and evolution. Positive and negative masses therefore tend to be mutually exclusive. In the solar system, positive mass dominates and negative mass density is extremely low, but not zero. We can thus consider that the Sun is at the center of a spheroidal gap in a very rarefied distribution of negative mass. Such a gap generates a very weak gravitational containment force. It is a weak force that is responsible for the deceleration experienced by the Pioneer 10 and Pioneer 11 space probes. This phenomenon, unexplained, is therefore a further confirmation of the Janus model. In another vein, researchers have constructed what they consider to be a mapping of the distribution of dark positive mass matter. They did this by using the fact that the positive gravitational lens effect tends to distort the images of galaxies in an azimuthal direction, figure on the left. On the contrary, negative mass distributions tends to induce radial deformations as shown in 2013 by the Japanese Koki Izumi, Shiazaki Agowara, Koki Nakajima, Katao Kitamura, and Hideki Asada. This would allow to map the negative mass by decoding this weak lensing. Perlmutter, Schmidt and Rice were awarded the Nobel Prize for showing that the expansion of the universe was not slowing down but accelerating. Friedman's models, all of which describe a deceleration of expansion, cannot therefore explain the observations. The same is true for Dirac-Milne's model, advocated by Chardin and Benoit Lévy, where expansion takes place in a linear fashion. The current model mainstream, lambda CDM, reports an acceleration of expansion attributed to a mysterious vacuum repellent power. The curve then takes the form of an exponential. An expansion attributed to a mysterious dark energy, negative, whose dominant relative importance is illustrated on this diagram. The fraction corresponding to the observable part of the universe then falls to 4%. The Janus model also explains this acceleration of cosmic expansion, cosmic dynamics being dominated by a majority of negative mass content corresponding to the same percentage. See drawing. The geometry then corresponds to a bending index k equals -1. The model, unlike the lambda CDM model with an exponential growth, predicts that the exponential will tend towards an asymptote. It asks the size of the universe will tend toward linear growth as a function of time. In 2018, Gilles D'Agostini compared the model with the most recent observational data from 700 Type 2a supernovae with excellent agreement. In the figure, the continuous red curve corresponds to the Janus model and the dashed curve to the lambda CDM model. The negative world is also expanding, but its movement is then the seat of a deceleration. The shape of its evolution then corresponds to a Friedmann's solution with a curvature index k equals -1 hyperbolic, which also tends towards an asymptote. But this belongs to the world of the negative masses and does not lend itself to direct observation. It is a fact today that many cosmologists, astrophysicists, and theoretical physicists concentrate their research on theoretical constructions which are also highly speculative and end up losing contact with any observable reality. Examples: string theory and the idea of a multiverse. Conversely, the Janus model intends to be anchored on these observational facts. We are now ongoing to address another observational aspect, the extreme homogeneity of the primitive universe. How did this information get to us? When information reaches us from more and more remote parts of the universe, it also emanates from an increasingly distant past. The message, due to the cosmic expansion, is undergoing an increasingly pronounced redshift. Advances in astronomy reflect this double plunge into distance and time. When leaving the visible domain, astronomy must first be combined in the infrared, which represents a first technical difficulty that must be managed with space telescopes. Beyond infrared and far infrared, we enter the domain of radio waves with frequencies, for example, centimetric. Capturing images at such wavelength sends us into an extremely distant past of the universe. With such a wavelength window, the light emitted by stars and galaxies is no longer captured. Such a device, placed aboard the Kobe satellite, launched in 1989, gives us the aspect of the universe when it was 380,000 years old. This is the face of the universe at this time. You're used to another image, this one where there are inhomogeneities. But these could only be achieved by artificial contrast enhancement using a computer. The true face of the universe at that time was this one. We'll deal with the inhomogeneities later. For now, let us concentrate on this fact of observation, the extreme homogeneity of the primitive universe to within 100,000. In cosmology, the primitive universe, when it was less than 380,000 years old, is considered a gas. More precisely like a plasma, since its temperature is then higher than 3000 degrees. The hydrogen, which constitutes the majority of it, is thus completely ionized. It is important to clarify and explain why we cannot obtain direct measurements, direct information relating to this primitive phase. Indeed, our only information is conveyed by light, electromagnetic radiation. In all frequencies, it is by photons. They manage to travel 13 billion light years without interacting with the atoms they encounter along the way. Seen from this angle, the universe is therefore extraordinarily uncluttered and transparent. But when we want to pick up messages from matter older than 380,000 years, it's no longer possible. This is because photons interact strongly with matter, mainly with the free electrons of the cosmic plasma. What emerges after each collision is no longer the original message, but the one conveyed by another photon, which is re-emitted after absorption of the first one. It's a bit like a messenger who, not being able to deliver his message himself, sees it copied at each step with calligraphy errors. Thus, when the message reaches its destination after such a chaotic journey, it has become totally blurred, unreadable. The information that refers to this primitive state of the universe boils down for the moment to three data that tells us, in the past, the temperature of the cosmic furnace had been much higher. There is what emerges from the content of the universe. Apart from what has combined to make stars and planets, apart from hydrogen, there is also 25% helium. Its presence is a sign that there has been a primordial nucleosynthesis where hydrogen nuclei has fused together to form helium. In order for this to have been possible, the temperature of the cosmic furnace at an earlier time must have been comparable to that which prevails when a thermonuclear device explodes. This is considered proof that the universe had previously experienced such a temperature. We then see the existence of what can be considered as the ashes of another cosmic reaction. These are the very many photons that makes up what is known as the background fossil radiation. The cosmological model proposed by Einstein was based on the observational data that the Newtonian model could not account for, the advance of Mercury's perihelion. The description of the universe by its equation reflects this, just as it is the basis of the gravitational lens effect. Later, the unsteady solution found by the Russian Friedman helped to explain another fact of observation, the cosmic expansion discovered by Edwin Hubble. From this vision of the world emerges an essential point. The oscillations represented by the photons constitute the wealth of the vacuum of space itself. As a result, these photons expand at the same rate as space itself. It's another facet of the redshift phenomenon. In 1965, Penzias and Wilson discovered isotropic radiation corresponding to a furnace temperature of 2.7 Kelvin, which corresponds to a wavelength of half a centimeter. This radiation, in fact, corresponds to a phenomenon occurring in the first hundredth of a second, corresponding to gamma rays resulting from the annihilation of matter-antimatter couples. Due to cosmic expansion, the measurement of this radiation at the present time corresponds to these radio waves of centimetric wavelengths. Although we do not have access to this phenomenon of massive annihilation of antimatter-matter couples, much earlier than this barrier being 380,000 years old, the observation of the existence of this ash allows us to deduce that this phenomenon took place. Let us note, by the way, that at this time the temperature of the cosmic mixture is hundreds of billions of degrees and is located when the universe is hundreds of a second old. It is on the basis of this observation that we can deduce the history of the universe between 1/100th of a second and 380,000 years. But, as Nobel laureate Steven Weinberg noted in his book, The First 3 Minutes, everything that has been said and written about the history of the universe prior to this first hundreds of a second is pure speculation and is not based on any observational evidence. Let's review what we can deduce about the past of the universe from observations. When the universe is 380,000 years old, its temperature is 3000 Kelvin, and after the medium deionizes. It was discovered in 1989 that this radiation has a very high homogeneity, to the nearest 100,000ths. The question of its very low inhomogeneities will be examined later. When the universe is 1 minute old, its temperature is on the order of 1 billion degrees. A primordial nucleosynthesis takes place which gives birth to helium, 4 hydrogen nuclei giving 1 helium atom. It is the lowering of the temperature that stops this fusion reaction and prevents the content of the universe from transforming entirely into helium. As a result, the mass content of the universe corresponds to 75% hydrogen and 25% helium. Further back in time, when the universe is 1/100th of a second old, the temperature reaches several hundred billion degrees. Later, when this temperature drops and the collisions between photons can no longer produce matter-antimatter pairs, a fantastic annihilation of this pair occurs. Fossil radiation is the trace, the proof that this phenomenon has occurred. Beyond this age of 1/100th of a second, let us keep in mind that everything is then made up only of speculations that are not based on any observational fact. We are now going to concentrate on this observation fact that constitutes the extreme homogeneity of the primitive universe. By homogeneity, it is necessary to enter that in all the regions of the universe accessible to the observation, one finds to the 100,000s the same values for the density and the temperature. For a gas to be able to present itself in this way, its different region must have been able to exchange momentum and kinetic energy by collision of its elements with each other. A paradox is emerging. For two neighboring particles to have been able to exchange anything, it can only be through an interaction of an electromagnetic nature. That is to say, with the help of photons. However, if we consider the speed of light as an absolute constant, when we go back in time, we obtain conditions where particles move away from each other at a speed greater than the speed of light. When one tends toward the moment zero, this speed tends even towards infinity. What we read on this curve is that after a certain amount of time, the electromagnetic wave emitted by a particle at time zero will reach its neighbor. Before, the evolution of the universe takes place without its element being able to interact with each other. Let's give an image. Let's imagine villages on an expanding planet. So the distance between two neighboring villages would increase over time. Each village sends a rider with a message. But the horseman's speed is less than the speed at which the villages are moving away from each other, because of this dilation of the planet. Surprisingly, despite this phenomenon, the inhabitants of these villages all speak the same language, have the same customs, even though they have never exchanged a word. The sphere representing the extension of an electromagnetic wave emitted from any point at time zero is called the cosmological horizon. This paradox, stemming from the homogeneity of the primitive universe, is thus the paradox of the horizon. In 1989, the Russian Andrei Linde proposed to solve this enigma by suggesting that the universe experienced an expansion of unprecedented violence at t equals 10⁻33 seconds, which then expanded by a factor of 10 to the power of 26, 1 with 26 0. A theory which was then given the name of inflation. The responsible for such an expansion would then be the field created by the mysterious and hypothetical particle, to which were given the name of inflatons, which at the end of this phase of inflation would miraculously transform themselves into quarks and antiquarks. But no one has been able to give an inflaton model that describes the process by which these particles could be transformed into a pair of quarks and antiquarks. The only justification for such a weighty hypothesis is that it is consistent with the only observational data available, namely this extreme homogeneity of the primitive universe. This pseudo-theory has been part of the standard model for 30 years because no other theory has been found. However, the Janus cosmological model offers another explanation. To solve this paradox of the horizon, it would be sufficient to consider a variation of the speed of light, which has been higher in the past. If then the variation of the cosmological horizon with its variable speed of light could follow the phenomenon of cosmic expansion at the same rate, the problem would be solved. This would ensure the homogeneity of the universe at all times in its history. At the time of the Big Bang, the speed of light would simply have an infinite value. But such a variation in the speed of light makes problems of all kinds emerge immediately in theoretical physics. Many physical phenomena predicted by the equations and where characteristic quantities occur, where the value of the speed of light is present, could no longer take place satisfactorily. Yet, as early as 1988, the French astrophysicist Jean-Pierre Petit presented in the high-level journal Modern Physics letter A scheme where it was no longer just the speed of light that varied, but all the constants of physics together. These basic constants of our physics are very few in number. We have c, the speed of light, h, Planck's constants, g, the gravitational constant, e, the elementary electrical charge, m, the elementary mass, mu0, the magnetic permeability of vacuum. The other constants are derived from this. Let's take the dielectric constants of vacuum epsilon 0 as an example. It is deduced from the magnetic permeability and the speed of light through the relation c equals 1 on root epsilon 0 mu 0. So there is a connection between the three constants. If we give ourselves the value of two of them, the third one is immediately deduced. Have there been other attempts based on a variation of the speed of light? The answer is yes. The Canadian Moffat in 1992 and the Portuguese Magueiro in 1998. But very quickly, all of them were confronted with all the unmanageable impacts related to variation of c. But since 1998, it is for 32 years, nobody seems to have taken up this idea of the joint variation of all constants of physics for lack of having understood it. How to make our physics adjust to variations of these constants? It is simple. All it takes is that this is joined with an invariance of all the equations of physics. These equations, what are they? Once again, there are a finite number of them. We've got, for quantum mechanics, Schrödinger's equation, the general relativity equation, it est Einstein's field equation, the fluid mechanics equation, Boltzmann equation, the equations of electromagnetism or Maxwell equations. Some will say, what about the 5 Navier-Stokes equation of fluid mechanics that translate the conservation of mass momentum and energy? A specialist in the kinetic theory of gases, of which I am one, will tell you that these 5 equations can be deduced from Boltzmann equation. A favorite subject for the French mathematician Cédric Williani, who won a Field Medal for his work on this equation, but who unfortunately abandoned mathematics for politics. These equations contain the constants in question, but also include space variables and time variables. For the invariance of the equations to be ensured, these quantities will also have to vary. Theoretical physicists call it gauge variations. We're going to add 2 scale factors, one designated by the letter r for the space variables, and another designated by the letter t for the time variable. We must therefore consider joint variations of these quantities corresponding to a generalized universal law of gauge, which is a fundamental property of our physics. Details of the establishment of this generalized gauge relationship can be found in a paper I published in the journal Astrophysics and Space Science in 1995. The frame of the calculation is also given in the appendix of the comic book Faster Than Light. It's an album that you can download for free in your own language by going to the Savoir Sans Frontières website. As these quantities are linked, it is enough to choose one of them as a guiding parameter to obtain all the others according to this last one. Let's choose the large scale factor r, which we know that its growth from 0 will reflect cosmic evolution. It is found that the speed of light c varies in 1 over the square root of r. Planck's constant h varies as r to the power of 3/2. The large gravity constant g varies as 1 over r. The elementary electric charge varies as a root of r. The elementary mass as r. The magnetic permeability of the vacuum also varies as r. From this, you will be able to make this calculation that the dielectric constant of the vacuum, epsilon 0, behaves then as an absolute constant. To that, it is necessary to add the variation of gauge of the timescale factor t, which varies then like r power 3/2. Thanks to this, we can calculate the evolution of the cosmological horizon with a speed of light that is infinite in t equals 0, then decreases accordingly to this law in 1 on the root of r. We then find that this horizon varies like r, which is what we wanted. The homogeneity of the universe is thus ensured at all scales, and we no longer need the inflatants and this heavy assumption of inflation. For the record, it was the theoretical physicist Alan Guth who first proposed the idea of inflation in 1979. According to the description of the behavior of the primitive universe that was fashionable at the time, it should have given rise to magnetic monopolies, which are like small magnets with a north pole without a south pole, or the reverse. It should be pointed out that these descriptions correspond to everything that is referred to when one tries to go back in the past beyond the first hundredths of a second. A totally speculative and problematic approach, devoid of consistent observational support. According to Guth, this idea of inflation could be justified by the fact that the existence of such monopolies was not observed. On this subject, the English astrophysicist Martin Rees adds, "Those who are skeptical about this exotic physics might not be very impressed by this argument, which explains the absence of particles that remains hypothetical after all. Preventive medicine can quickly be recognized as being 100% effective in dealing with a disease that has never been observed before. There is another aspect on which the proponents of inflation theory rely, the idea that today's universe is geometrically flat and free from curvature. This is not a local measurement of curvature, but it is deduced from the model where the speed of light is constant. This argument falls with the variable speed of light. So here we are with an evolution of the primitive universe that takes place in such a way that the equations of physics remain invariant. We can try to imagine a device that allows us to highlight these variations in the constants. But this one, constructed with the same equations, will derive, one would say, parallel with these constants that is supposed to measure. The experimenter or observer is then similar to a man placed in a room where the temperature is rising, as indicated by the thermometer hanging on the wall of the room, would like to demonstrate the expansion of an iron table by using a ruler made of the same metal for this measurement. He will not be able to highlight this variation in length. But then, what's the observable? It's very simple. It boils down to the homogeneity of the environment. However, there is still a serious problem. Indeed, this evolution with constant variables presents the particularity of conserving energy in all its forms. Let us add in passing that all the characteristic lengths varies as r, and that all the characteristic times vary as t. However, the redshift phenomenon is based on the measurement of the energy loss of photons during their pass, which is linked in a scheme with absolute constants to the fact that their wavelength distance at the same time as r. The energy is E equal to hc on lambda. Do the maths. H varies on r to the power of 3.5. C varies as 1 on the root of r. Lambda varies as r. As a result, the variation of the constants invoked make this energy conserve itself. If this dynamic with variable constant was maintained today, the observation would not show any redshift. We must therefore consider a scenario where these constants vary in a primitive epoch, resulting in the homogeneity of the universe, but that this epoch leads to a stabilization of the constants. Question: when would the transition take place, the change of regime? In quantum mechanics, particles are assimilated to wave packets that have a certain extension in space. Consider a medium made up of hydrogen atoms consisting of a single electron orbiting a proton. Although this representation is simplistic, since in fact this electron is not locatable on this alleged trajectory, we can calculate the radius of this orbit by writing that the centrifugal force exerted on the electron is compensated by the Newtonian force of the electrostatic attraction exerted on it by the proton positively charged. We then obtain the radius of this hydrogen atom, so-called Bohr's radius, which is worth half an angstrom, or 5·10⁻11 meters. The orbit speed of this electron around the nucleus, which can be summed up as a proton, is then of the order of 2,000 kilometers per second. It is 2 orders of magnitude less than that of light. The wave associated with the existence of this electron as an object orbiting around this proton corresponds to de Broglie's wavelengths, h/mv, where m is the mass of the electron and v this orbital velocity. As a general rule, this de Broglie length is the order of magnitude of the diameter of the atoms. For atoms to exist, there must be enough room for the waves corresponding to the different states or modes to take their place. When the density in a certain medium becomes so high that the space available for each of its components becomes too small to accommodate the undulation that characterize them, they simply cease to exist. Consider a neutron star. The density of its components increases as we go deeper into its core. On its surface, there is still enough space for the matter to be in the form of atomic nuclei. The surface of nucleon stars is considered to consist of a layer of iron 1 meter thick. When you go deep into the star, there's not enough room for the atoms to exist. The atoms are then dislocated, and the matter is then in the form of a plasma consisting of protons, electrons mixed with neutrons. The wavelength associated with the existence of the free particle is then what is called the Compton wavelength, which is h/m that multiplies c. It varies as the inverse of mass. If this wavelength can be equated to the size of the particle, the portion of space they occupy, then the electron is 1,850 times larger than the proton and neutron, since it has 1,850 times less mass. In order for an electron to exist, to caster its wave function, it will need 1,850 times more space than for protons and neutrons to exist. So when we go into the neutron star, the electrons will eventually disappear, combining with the protons to give neutrons, forming the heart of the star. When we go back in the past of the universe, the density of the cosmic medium also increases. But things do not happen exactly like that, because protons, neutrons and electrons bathe in the middle of photons, which are a billion times more numerous. The cosmic fluid is made up of what is called matter energy, which comes from the form of masses, that of protons, neutrons and electrons, and in the form of radiation. We first come across a phase immediately before the fateful 380,000 years, where energy is mostly in the form of radiation. Indeed, the further back in time we go, the more energy photons represents, since their wavelength varies like the R extension of the universe. There comes a time when even the most massive particle in the mixture can no longer exist because the distance between them becomes less than their Compton distance. Beyond that, the Compton distance must be reducible. We then enter this regime with variable constants, where this Compton length then varies as r. Let's reverse the direction of this story. When the density is very high, the evolution takes place in a regime of variable constants. After a while, the distance between the elements becomes sufficient and the constants then asymptotically acquire the values we know them today. This corresponds to the curves in the figure. By the way, we notice that at the time of the Big Bang, the speed of light and the constants of gravitation tend towards infinity. Conversely, Planck's constant, the elementary electric charge, the masses, the magnetic permeability of vacuum tends towards zero. As we have already said, in the cosmological Janus model, we always start from an observational datum. Thus, this modeling with a regime of variable constants was introduced in a primitive phase to account for the extreme homogeneity of the universe. This allows us to dispense with the hypothesis of the existence of inflatons. Still relying on the joint solutions of the system of coupled field equations, Janus. So we get two parallel stories. The first to highlight the theme of parallel stories was the German Sabine Hossenfelder in 2008 article. So there are two different histories, depending on whether the phenomena are observed by positive mass or negative mass observers. This is reminiscent of the famous myth of Plato's cave, but with two observers looking in two different directions. On two different parts of the cave wall, they see dancing shadows representing two different shows from the same projection system. This twofold evolution is obviously a little difficult to understand. The observer made of positive masses sees only galaxies forming an incomplete structure of matter. For him, the universe is expanding at an accelerated rate. He has a certain perception of distances which corresponds to a scaling factor R+. For him, all movements is limited by a light speed, c+. The world seems to be populated by stars, planets, and a wide variety of atoms and molecules, obeying a physics constructed from the constants c+, h+, g+, e+, m+, and mu0+. There are also living beings. This observer evaluates the age of the universe with a value t+. The field of its observation is then limited to a large cosmological horizon h+, limited in scope. The observer, made up of negative mass, sees only a regular distribution of spheroidal objects with blurred contours emitting in the red and the infrared. In his vision of the world, there are only antiatoms of hydrogen and helium. There are no stars, planets, nor galaxies. His negative world is expanding at a snail's pace. This observer, consisting of negative masses, evaluates distances with a scale factor R-. The velocities there are limited by a value of the speed of light c-, consisting of photons of negative energy. The physics of these negative masses obeys the same set of equations equipped with the constants c-, h-, g-, e-, m-, and mu0-. It evaluates the age of the universe at a value t-. There is also in this negative world a great cosmological horizon h-, which is also of infinite extension. There is one thing I think you must have understood. It is this profound asymmetry that exists between these two sides of the universe, its positive side and its negative side. In cosmology, this idea of the appearance of things, space and time has long been introduced, with an inseparable link between what is observed and the notion of the observer. We classically use the word facies of the universe. Facies means face. The universe presents us with two different faces. That's why the name Janus universe is adaptly chosen. But instead of this image, we should imagine something like this. The Janus cosmological model is the only one based on this profound asymmetry between the world of positive and the one of negative masses, an idea that totally escaped Sabine Hossenfelder. That's why she could not go any further after her trial in 2008. But this asymmetry, where does it come from? Immediately after the Big Bang, the two universes evolve with the same set of constant variables, C, H, G, E, M, mu0. But such a universe with constant variables is violently unstable. These two worlds then diverge exponentially, and two sets of parameters are created referring to these two worlds, positive and negative, which differ in every way. It is the same physics with the same set of equations, but equipped with different constants and scale of factor of distance and time. The times t plus and t minus are different. The distance scales r plus and r minus are different. The speeds of light c plus and c minus are different. The material densities arrow h0 plus and arrow h0 minus are different. Based on observational aspects such as the large-scale structure, the structure of galaxies, the acceleration of cosmic expansion, the gravitational lens effect, we were able to evaluate this difference, and since the positive masses only accounted for 4% while the contribution of the negative masses was 95%, we were able to evaluate the difference between the two. In this double evolution, things are linked. Thus, the ratio of the speed of light c plus to c minus is equal to the square root of the ratio r minus to r plus. We thus know that with respect to a path to be carried out between 2 points E and B of the universe, there are two different paths, according to whether this path is driven with an object made of positive mass or with an object of negative mass. You know that in cosmology we consider the universe to be a four-dimensional hypersurface. We'll take the analogy of this hypersurface. Now I have a two-dimensional surface. This surface has a front and a back. Here I have represented 2 points on this surface that are distinct. These points A and B are present both on the front and on the back. So there are two ways to join them, depending on whether you trace the segment on the front or on the back. Here I've marked this route on the front with a red line. The path on the back will be represented by a blue line. Now, if I want to make length measurement on a surface, I will have to use a ruler. I'll take one of these, this one, and the other one, that one. Thanks to this, I will draw two different grids on the front and on the back, and this is what it's going to give me. On the front, between A and B, I have 18 graduations, so the length is 18. However, on the back, I have 3. I deduce that the distance AB, when measured on one side, is 18, and on the other side is 3. So on this other side, that distance is 6 times shorter. Let's go back to our image of the myth of the cave. One of the pictures is this one, and the other image is that one. At that point you ask, what's the projection device? I'll show it to you. That's it. Let's move to our four-dimensional hypersurface. The distances to be traveled are in the ratio r plus to r minus. We know that the distance covered in the negative slope is much shorter. Along these routes, speeds are limited to the speed of light. These are different. It is known that C plus is higher than C minus. By the virtue of the gauge relationship, C minus over C plus equals root of R plus over R minus. And we will rely on the analysis of the very small fluctuations in the fossil cosmic radiation background. Here again, the interpretation we will give will be completely different from what is in vogue in the scientific community. Here is a phenomenon first described by the English astrophysicist James Jeans called gravitational instability. It is this phenomenon that causes matter to spontaneously tend to form lumps separated by an average distance called the Jeans length. I refer you to one of my albums, which can be downloaded for free on my website, Savoir Sans Frontières. This is the address of my website where you can download for free my albums translated in 40 languages. The explanation of gravitational instability can be found on page 12 of my album Mille milliards de soleils. Here in French, in Spanish, in Italian, in Russian, in English, in Arabic, in Czech, etc. Gravitational instability is, in principle, supposed to concern only matter. But in fact, what is concentrated in the form of lumps is energy, whether it is existing as matter or radiation. It is written black on white in Einstein's equation. Photons contribute to the gravity field through their equivalent gravitational mass. m(phi) equals h nu on c squared. If in one region of space a concentration of energy in the form of radiation were to build up, and if this concentration persists, then it would be the expression of the manifestation of gravitational instability in a radiation field. No one has ever considered such a possibility. The reason is simple. The corresponding length of genes along which the fluctuations would register would then be identified with the cosmological horizon large H plus. Such fluctuations would then be beyond our observation capacities. These fluctuations in the radiation field also occur in the negative world, and also their observation would be inaccessible to an observer made up of negative mass, since they would be beyond its own cosmological horizon, large H minus. But it turns out that H minus is smaller than H plus. As the two sides of the universe, its front and back, interact through gravitation, these fluctuations of the radiation field occurring in the negative world with a wavelength H minus cause a weak response in the positive world. This is our interpretation of the fluctuations observed in the fossil radiation. If the fluctuations of the negative world are reflected in the positive world by giving their imprint, the reverse is not true. The radiation field inside the small horizon sphere is perfectly homogeneous. These fluctuations occur when the universe is in its primitive states, in the phase with variable constants. Beyond the horizon, the set of parameters C, H, G, E, M, mu0 fluctuates, therefore. It is the intuition of this kind of phenomenon that gave birth to the concept of the baby universe. We thus have a series of universes endowed with their own sets of constants, but which would be regulated by the same set of equations, Schrödinger, field equation, Boltzmann, and Maxwell. Moreover, these fluctuations are probably of limited magnitude. Even if we cannot make observations of these neighboring universes, they would thus normally experience similar histories, with births of galaxies, stars, planets, atoms, with the same Mendeleev table from the baby universe to another. This vision departs from the idea of an exuberant infinity of universes where everything would be possible, conceivable, which appeals to many cosmologists today. Still, these fluctuations refer to the early universe when the cosmological horizon H plus and H minus grow as the scale factor R plus and R minus. Measuring the characteristic wavelengths of the fluctuation gives us access to the ratio of the scaling factor R plus under R minus, which is then of the order of 100. We deduce that the ratio of the speed of light, c minus over c plus, equals the root of R plus over R minus, is of the order of 10. Thus, if the speed of light is 300,000 kilometers per second on our side of the universe, it is of the order of 3 million kilometers per second on its negative side. If we one day have a technique that allows us to revert the mass of a vehicle and its occupants, it would allow us to travel via this negative world to other nearby star systems in a duration 1,000 times shorter than if we were traveling on the positive side of the universe. As objects of negative mass are invisible to positive observers, when such a nave would perform its mass inversion, it would seem to dematerialize before their eyes. At the end of the journey, a new mass inversion would allow the nave to belong again to the positive universe we live in. For an observer, it would seem to materialize suddenly by emerging from nothing. Until now, we have always answered our theoretical developments to observational data and use them as a starting point. Let's move to the speculative aspects of time. What is extraordinary in cosmology is that because light takes time to reach us, any observation gives us immediate access to the past. We can, thanks to this, go back to the time when the universe was 380 years old. But as we have pointed out, it is impossible to have information coming directly from an earlier period. We can only attempt an hypothetical reconstruction of this more distant past on the available remnants of fossil radiation and the 25% of the mass content of the universe in the form of helium. But, as Weinberg pointed out, the writing of the cosmic scenario prior to the first hundredth of a second remains as random as ever. In fact, we do not know what the universe was made of in that earlier time. We can only imagine that going back even further into the past, the temperature continues to rise. One way of trying to approach this reconstruction of the past has therefore been to increase the particle velocity in experiments conducted on particle accelerators. It is easy to estimate the energy required to make a particle of mass m appear. We can rely on the relationship mc² equals kT, where m is the mass of the particle, c the speed of light, T the absolute temperature, and K the Boltzmann constant. For the antiproton, this temperature is around 10,000 billion degrees, but we are used to convert this temperature into electron volts, and this gives a MeV, a million electron volts. In 1955, it was thus possible to create antiprotons in the Large Accelerator at Berkeley. Nothing then prevents us from considering even higher energies and therefore even higher temperatures. Bearing in mind that in a particle accelerator only the thermal agitation speed of a gas brought to an absolute temperature T is reconstructed, not its density. In the CERN collider, this energy and equivalent temperature was increased to 7 tera electron volts. Tera means monstrous. In temperature, it represents 70,000 million degrees, a figure that no longer speaks at all to the imagination. This was to allow the materialization of new particles that were supposed to represent the content of the universe when it was heated to such a temperature. These experiments were supposed to produce what had been called superparticles, an extension of classical theory called supersymmetry. But these experiments ended in complete failure. Consequently, this confirms Weinberg's point. The description of the universe prior to the first hundredth of a second still remains a mystery. Talking about time is just problematic. As has been said, the absolute temperature of a gaseous medium is nothing more than a measure of the kinetic energy of the thermal agitation of its components. When this temperature rises, the speed of the components eventually approaches that of light. We know that when the speed of objects approaches that of light, the time attached to them tends to freeze. Under these conditions, out of which materials can a clock be made? And if this conception of a clock becomes impossible, what physical meaning could be given to time? What is time? For us, a minute is the time it takes for the second hand of our wristwatch to go around. An hour is the time that elapses when a small hand of this wristwatch also makes a turn. One day, it's a circumnavigation of the Earth. A year is a circumnavigation of the Earth around the Sun. In other words, time is an angle. It is measured in numbers of revolutions. We can then imagine a conceptual clock consisting of two masses orbiting around their common center of gravity. The rotation period of such a system is then 2πr power 3/2 on gm, where r is the orbit radius, g the gravitational constant, and m the mass. When we go back to the supposed zero instant and consider a regime where the quantities mass, gravitational constants, and orbit radius are absolute constants, our elementary clock will make a finite number of revolutions. This corresponds to the classical conception of time in cosmology. On the other hand, if we consider that this period corresponds to a regime of variable constants, then the radius of the orbit varies as r, g, gravity constant, varies as 1 on r, the mass varies as r, the period of rotation varies as r exponent 3/2 and tends towards zero when we try to approach the Big Bang when r tends towards zero. If again we identify time with the number of revolutions of our elementary clock, then the ascent to the Big Bang takes place in an infinite amount of time. It evokes that Greek myth where a child tries in vain to catch a turtle. As a transposition, a child then tries to approach the zero instant. Unfortunately, the closer he gets to that point, the older he gets. He dies before he gets to that point. Another image consists in assimilating the universe to a book open to a page representing the present. The character then tries to flick through this book backward to try to find his way back on his first page, seeking for a preface where the author would have recorded his intentions. But when he tries to get closer to this page 0, the sheets of the book become thinner and thinner. Their thickness tends towards 0, which makes access to this page impossible. Each page contains a text made up of sentences and words whose layout reflects the constraints imposed by the laws of physics. But gradually the words come together and form a text in which one ends up no longer being able to detect any meaning whatsoever. As the character flips his pages backward, they are only made up of series of randomly distributed characters such as the Hebrew tohu bohu. By the way, one may find it problematic to want to question the way in which time goes through, at a time when the universe has no order or structure of any kind, and when no creature can exist to live within, be aware of it, and care about it. A last remark concerning the geometrical structure ensuring the connection between the two universe sheets. The singularity can be eliminated by replacing it with a state of maximum density where the time sag would be reversed along with mass and energy. Whether this connection is made by means of a singularity or by this sort of space bridge, we will note that the question of a before Big Bang disappears. We will now briefly discuss the impact of the model in the field of quantum mechanics. Classically, it does not support negative energy states. In quantum field theory, the negative energy states that could emerge from space and time inversion operators are immediately eliminated by making an ad hoc choice of these operators. This is described in Steven Weinberg's book, The Quantum Theory of Fields, starting from page 74. But at that time, the scientific community considered as an established fact that the expansion of the universe was taking place in an accelerated manner, rewarding this work with the Nobel Prize in Physics awarded to Perlmutter, Rice, and Schmidt. However, this acceleration is a sign of the action of a negative pressure resulting from a sum of negative energy states. The study of these states is therefore once again based on observational facts. In 2018, the Belgian mathematician Nathalie Deberg published an article in the communication section of the Journal of Physics showing that these states were naturally derived from the Dirac equation equipped with a linear and unitary time inversion operator and not an antilinear and anti-unitary one. In 2019, Canadian theoretical physicist Benoit Guy published a second article along with these lines. These first papers open a rich field of investigation in the field of quantum mechanics, likely to lead to a mass inversion technology. After having presented the main features of the Janus cosmological model in this long presentation, we will now summarize its achievements. The model demonstrates the crucial importance played by the negative mass and energy particles in cosmic dynamics. Their introduction imposes a profound change in the geometric paradigm by replacing Einstein's classical equation by a system of two coupled field equations. This system avoids the runaway effects. The model fits with all the local relativistic experimental data, Mercury's perihelion advance, and deviation of light rays by masses. Through an exact solution, it accounts for the acceleration of cosmic expansion. It accounts for the fold structure of the universe on a large scale. It explains the nature of the Great Repeller phenomenon discovered in 2017. It accounts for important gravitational lens effects. It explains the structure of matter in filaments and clusters. It proposes a new scenario for the birth of galaxies. It explains the confinement of galaxies. It accounts for the flat shape of their rotation curves. It explains why distant galaxies at strong redshift have low magnitude. It accounts for the high speeds of galaxies in clusters. It gives an account of the phenomena of gravitational marriages. It provides an explanation of the structure of spiral galaxies. It explains the great homogeneity of the primitive universe by introducing a new vision of it in a regime with variable constants. It gives an alternative interpretation of the fluctuations observed in the cosmic background as an imprint on the positive world of fluctuations in the negative world, resulting from the gravitational instability in this environment. It deduces from their analysis the ratio of the scale factor of the two sides of the universe as well as the ratio of the light speeds within them. It suggests the possibility of making trips to other star systems using negative slope geodesics with the consequent reduction of travel time by a factor of 1,000. It provides an explanatory scenario of the lack of observation of primordial antimatter, giving substance to the ideas of Russian Andrei Sakharov. The duality of antimatter being present in the world of negative masses, this leads to the existence of two antimatters, one C-symmetrical of positive mass and the other PT-symmetrical of negative mass. The model fully defines the identity of the invisible components of the universe: antiprotons, antineutrons, and negative mass antielectrons. This antimatter of negative mass, emitting negative energy photons, travels on the geodesics of the second metric, that is to say, on sets of disjointed trajectories with respect to the positive masses. This explains the invisibility of such structures. The model predicts that in the alpha and G-bar experiments being set up at CER, antimatter will behave in the Earth's gravitational field like ordinary matter. The Janus model points out the need to include negative energy states in quantum mechanics and in the quantum field theory. It eliminates the pre-Big Bang issue. It proposes a redefinition of cosmological time in the primitive phase of the universe. It describes the contents and structure of the universe of negative masses. Alternatively, although an explanation has been proposed based on the operation of the probes and explaining the slowing down of the space probe Pioneer 10 and Pioneer 11, The model proposed an alternative interpretation of this slowing down due to the gradient of the very small amount of negative mass surrounding the solar system. French-speaking internet users who want to know more will be able to refer to the 30 videos of the Janus series that can be accessed by clicking on the link of the homepage www.gp-petit.org. Remember that these are equipped with English subtitles from Janus 13 onward. A question arose: why, despite numerous results obtained, is the support of scientists for this approach still so limited? This model invalidates a considerable body of work whose starting points were the hypothesis of the existence of positive mass, dark matter, vacuum, repulsive power, and a field of inflatance. It represents a profound paradigm shift with considerable repercussions in cosmology, astrophysics, particle physics, and general physics. Still, the very rare time when French scientists have expressed an opinion on the Janus model, either in interviews, videos, or books, it has shown that they have not taken the trouble to read about it and have made false statements signaling their total lack of understanding of the basis of this work and their ignorance of the results obtained and published in high-level journals. But the most important aspect is that this new vision of the universe opens up the possibility of being able to establish contact with neighboring star systems through the possibility of making journeys in a reasonable time using vehicles where mass inversion technology would be mastered. A prospect that could, for obvious reasons, provoke a powerful psychosocial-immunological response in many spheres, including within the scientific community itself. Since the publication of the first article describing this Janus cosmological model in 2014 in the journal Astrophysics and Space Science, what has happened in the scientific community? Strictly nothing. In France, because of this psychosocial-immunological mechanism mentioned above, the heads of the seminars of the French laboratories have responded with silence to all my proposal to present the model. From time to time, very primitive works linked to the Janus model are widely taken up by newspapers of all countries, eager for new works, but no one talks about our cosmological Janus model. 6 years have passed. Since I was born in 1937, I'm now 83 years old. Given the inertia of the scientific world, there is a good chance that nothing will happen in the next 6 years. I will then be almost 90 years old. The big problem for a scientist who wants his ideas and work to be recognized by the scientific community comes down to his longevity. If he is more than 80 years old, time becomes an unavoidable natural obstacle for him. There is then a high probability that he will be sitting on a cloud, seeing his ideas and work promoted under another title with other authors. Despite this observation, sad but realistic, I will continue during the few years that remains for me to live the work that I have undertaken both in astrophysics, cosmology, and theoretical physics. Applying Guillaume d'Orange's precept formulated in the 17th century, it's not necessary to hope in order to undertake, nor to succeed in order to persevere. I will also try, with the help of researchers with adequate means, to develop an experiment that can highlight the phenomenon of mass inversion. Now, at the beginning of the year 2020, the article published in 2018 by the mathematician Nathalie Deberg, already quoted, represents an interesting breakthrough of the Janus concept in the field of quantum mechanics. She is currently a teacher in a Belgian technical school. Unfortunately, her teaching and administrative workloads leave her little time for research. It would be important and helpful if she could concentrate full-time on the research she is doing with me. To do this, she would need to be relieved of her teaching and administrative duties. Her salary would therefore have to be paid at a given cost of €86,000 per year, including charges. In order to raise this money, we have built the Janus Support Association to collect donations. If you wish to contribute, you will find in the notes of this video a link to the association's website, where is displayed all the necessary information. The internet user may be surprised by such a formula, but whether it is France or Belgium, hoping for a solution from the institution would be a fiction.